Greetings, everyone. I know that folks are just joining into the webinar, so we'll give people just a few more minutes to join so that we get most everyone into the webinar before we get started. So thank you again, and from wherever you are, good morning, good afternoon, good evening. I know some of you are good late at night. So I hope you're all doing well. And today is an exciting day for IWCS. Our deadline for submitting abstracts is officially today. Next week, we're going to get together to review all of the abstracts and set up the preliminary program for our IWCS 2024 event in October. So if you haven't submitted an abstract yet, you've got a few more hours to do so. It's not a hard process, but we know that there has to be some extensions and things like that, various different reasons why. But again, if you're interested in presenting at the IWCS 2024 event in October, please go onto our website and use the simple information to submit an abstract or a topic for us to consider. So again, we'll just wait another minute and we'll go ahead and get started. All right, well, why don't we go ahead and get started? And again, I want to welcome you to today's IWCS webinar event. My name is Dave Cadu, and I'm honored to be your CEO of IWCS. And again, I'll be your moderator for today's event. A few housekeeping items for you to consider. As an attendee, you are part of a larger audience. So during the presentation, all participants will be in listen-only mode. So as a reminder, also, this event will be recorded for rebroadcast. So we encourage you to submit any questions or comments that you might have into the chat function. And that is should be in the panel on the right of your screen once you select the chat function. After typing your questions in the space at the bottom, hit the send button, and your questions will be addressed as time permits at the end of the presentation. Our IWCS webinar event is hosted by the Cable and Connectivity Industry Forum. And today we welcome Hariam Bhargava, who is a lead scientist for Corning at their research center in India. Hariam will be presenting his paper today on emissivity, a relevant parameter for burn testing according to EN 50399. So Hariam Bhargava received his master's degree in mechanical engineering from the Indian Institute of Technology in Bombay. He joined Mahindra Mahindra Limited as a senior engineer in 2017. Since 2019, Hariam has worked at the Corning Research Center in India as a scientist and models flow and thermal processes for various Corning businesses. So we welcome Hariam. He has delivered excellent presentations to IWCS in the past, and we're very appreciative of having him with us today. So welcome, Hariam, and go ahead and take over.
Yeah. Thank you, David. So hello, everyone. I'm Hariam Bhargav, and today I'll be discussing some of the work that we did recently on studying emissivity for the burn testing of cables according to the EN 50399 standard. So in this work was accomplished with in a team comprising of my colleagues Waldemar, Thomas, and Anish. So, let me discuss briefly the outline of today's talk. So I'll be starting with an introduction of the cable burn testing. We will then discuss some experiences from the past on burn results for the cables per the EN 50399 standard. We will then move to the observations in terms of discrepancies in burn test results obtained at different test facilities uh, in the European Union region. Uh, we will then go to some hypotheses uh, regarding uh, why these discrepancies might be occurring, followed by a discussion on experiments aimed at validating this hypothesis and their results. In the end, I will discuss some work related on theoretical modeling of the burn process, and I'll then summarize my talk discussing some potential next steps. So let me start with a brief introduction of CPR. So CPR stands for Construction Products Regulation. It is legislated by the European Union, and it governs all the requirements for different products that are used in construction within the EU. So cables uh, that riser cables that are installed in residential or commercial buildings fall under this category of being a construction product, and therefore they are covered under the CPR regulation. Within the CPR, there is fire safety component, which must also be satisfied by all products that come under CPR. So, uh, for the certification of fire safety of cables per the CPR, there is a fire burn test conducted, which is governed by the so-called EN 50399 standard. In this test, basically, an assembly of cables is tested in a burn chamber for a specified period, and as an outcome of this test, we monitor several parameters such as the vertical flame spread, total heat release, etc. So the figure on the right here shows a picture of an assembly of cables mounted on a vertical ladder at the end of the burn test, and uh, we focus on the charred portion of the cable along the height of this cable assembly, and the the height of the cable till which the charred region persists is termed as the vertical flame spread, shown by this area. Uh, as an outcome of the burn test, uh, we using the results in terms of flame spread, total heat release, etc. The cable is accorded a rating in terms of fire safety going from B2 through F using this test. So now let me discuss briefly the test apparatus used for the EN 50399 test. So on the right is a picture of the test chamber located at uh, the Corning's facility in Berlin. So in the left here we have the burn chamber in which we place the cables in front of a burner, and outside of the chamber we have several components supplying the air to the burn chamber, as well as studying the exhaust gases generated due to the combustion of the fuel and the cable material, and these are analyzed to quantify results such as heat release rate, etc. On the left is a cartoon showing the layout of the burn chamber. So within the burn chamber, we have a vertical ladder as shown over here, on which an assembly of cables is mounted, which is placed in front of a burner, and the burner is ignited, which leads to cables undergoing pyrolysis and combustion. So Corning has developed the so-called reference cable. The schematic of which is shown on the bottom left here. This cable can be is produced solely for the purpose of benchmarking cable burn testing for this standard. So this cable can be has three components as shown over here, and it can be manufactured with very good precision. Therefore, it eliminates any possibility of uh, deviations in burn test results from arising out of the cable composition. So these reference cables are made available to different locations uh, that perform burn testing to benchmark their processes. And the standard as it is recommends to use this cable for benchmarking any test setup. And I would like to also disclose that that all the experiments and the results that we will discuss in today's presentation pertain to the reference cable as shown over here. So now moving to some experimental observations on burn test results obtained using the reference cable within the EU. So on the left, we look at distribution of flame spread, vertical flame spread obtained from a round robin test performed in 2018 and 20. Uh, uh, these results showed an average of close to 1.4 to 1.5 meter of vertical flame spread with a sigma of about 0.2 meters. Whereas when the same cable was tested in accordance with the test standard at Corning's internal facility at Berlin, we found a significantly higher flame spread of about 1.8 meters. Uh, and this as the scale at the bottom shows, this deviation in flame spread obtained at from the round robin and the Corning's CTCB location, the difference is significant enough to cause a deviation in the cable rating from B to C. However, when we look at test outcomes from new chambers that are supplied that are provided by the same chamber supplier to different locations, we see that the results from these new chambers are uh, comparable to the results obtained at CTCB. So we have test results from different locations and the distributions average at a value of about 1.9 meters, which is close to what we obtain at CTCB at about 1.83 meters. So to assess, to investigate the reasons behind the deviations obtained at different different round robin tests and the results from CTCB, there's been a multi-year effort at Corning to understand why these deviations are occurring, and several factors pertaining to the ventilation of the chamber, the mounting of the cables within the chamber, and the burn chamber equipment have been done in the past. And so many of these studies have already been discussed at different IWCS events in the past as well. So uh, uh, and we have listed all these parameters over here, which Corning in its testing have investigated in the past, with also highlighting the impact of these different features. For example, in the first column over here, we had found that any change in the air distribution within the chamber has a significant impact on the flame spread, and this was presented in communications to IWCS earlier. Further, for example, if the uh, gap between cables as they are placed on the ladder changes, that also has a significant impact on the flame spread. Further, if the chamber has any leakages from the door, or if the chamber insulation has deteriorated, that can also impact the flame spread. Finally, if the burner the flame shape from the burner changes as a result of variation in the feed of fuel and air, the flame shape change can also result in a flame spread deviation. However, we would like to highlight that none of these variables that we tested as giving a flame spread change uh, are allowed uh, uh, are allowed in the in the current EN509 standard. So to rephrase, basically, all of these variables listed here, if they are maintained within the specifications from the standard, they do not explain the flame spread deviation that I showed in the last slide between round robin test and CTCB. So that led us to further investigate any other parameters that could impact the flame spread that we are seeing from these tests. So that led us to investigate some of our own internal test results over the years. So the plot over here shows change or a scatter distribution of flame spread results over several years of internal testing at the burn chamber in Berlin. So what we saw from these results is that as the burner was installed in 2015 and several burn tests were conducted, over here we are only showing results from the tests which were conducted in accordance with the EN509 standard, as in all the variables within during the conduct of these tests were per the standard. However, as time progressed from 2015 to 2021, and the number of tests, for example, and spread over almost 200 tests, we saw that the flame spread from these tests showed a distinct reduction as time progressed. So at the start of when the chamber was new in 2015, the average flame spread was close to 2 meters. After 6 years of chamber use, the average flame spread dropped to about 1.8 meters. The chamber was not modified in any sense to this period, so that this leads us to question what has changed in the chamber over this period, which shows this flame spread reduction. So this, after several inquiries into what has changed in the chamber over this period, we saw something obvious, which is the appearance of the chamber. So on the left is a picture of the chamber from when it was installed afresh in 2015. We see very shiny walls with highly reflective surfaces, and in the center we have the image of the same chamber from 2022. What we see is that the appearance of the walls has changed significantly. The walls have been accumulated with soot. They have become rough and they have gained a very dark appearance. So this led us to formulate a hypothesis that as the chamber aged over several years from 2015 to 2022, the emissivity of the wall surfaces of the chamber walls changed significantly. Essentially, in as the chamber aged, the inner walls of the chamber gained a very high emissivity, and when the emissivity of the chamber walls increases, they can absorb most of the radiation that is coming onto them from the high temperature flames generated from the burner. And as they have a high emissivity, they can absorb these radiations efficiently, and that leaves less amount of heat for the for heat transfer to the cables. This can reduce the amount of combustion of the cable material, resulting in a shorter flame spread. And conversely, when the chamber is new, the walls have a very low emissivity. They reflect most of the radiation that falls onto them, and therefore that leaves more amount of heat for the cable material to get pyrolyzed and combust. So essentially, the hypothesis is that the high emissivity results into a shorter flame spread, and the low emissivity results into a longer flame spread. So basically, then we pose the question of how does the flame spread depend on the emissivity, leading to formulation of experiments uh, uh, to be performed at CTCB's test chamber. So now we discuss some of the modifications that were required to be done to the chamber. So in the center, we are showing the chamber as it was in 2022 with dark soot deposited walls of the chamber as shown over here, and the flame spread obtained. And for the purpose of this experiment to assess the impact of emissivity, we did several tests again with the chamber as it was and obtained a flame spread of about 1.78 meters. Then to assess the impact of lower and higher emissivity, the uh, chamber wall walls were modified by fixing plates with very low emissivity as shown on the left and very high emissivity as shown on the right. So on the left, we installed thin, shiny plates on top of the chamber as it was, as shown in the center, which gave a very shiny appearance to the chamber wall, as shown on the left. And conversely, separate set of plates with very dark coating was prepared, and that was uh, uh, installed over the existing chamber, as shown in the center, to give the chamber walls a very dark appearance, as shown on the right. So, and the emissivity of the chamber walls was measured with a handheld pyrometer, and the approximate value of emissivity for the existing chamber was found to be in the range of 0.6. That for the chamber with coated plates was found in excess of 0.9, and that for uh, the emissivity measurements for the shiny plates is a little tricky because it's a very highly reflective material. So it showed an emissivity in the range of 0.1 to 0.4. So now after these new chamber wall emissivities were prepared for testing uh, in the CTCB burn chamber, several tests were performed for each of the conditions of the shiny and coated wall to find an average flame spread for both of these conditions. So when we tested the shiny chamber over several iterations, the average flame spread obtained from these tests was found to be close to 2 meters, specifically at 1.96 meters. And on the other hand, when we tested the chamber with coated or dark walls, it showed a very interestingly low value of flame spread at about 1.6 meters, specifically 1.5 meters. So when we contrast the chamber with shiny and coated walls, the difference in flame spread is very significant at 0.4 meters. So then we try to correlate the flame spread with chamber wall emissivity on this plot over here. We on the y-axis we consider the emissivity of the chamber walls for the three configurations discussed earlier, close to 0.4 for the shiny walls, about 0.8 for the existing chamber, and uh, close to 1 for chamber with dark coated walls. And they show and on the x-axis we show a flame spread, the flame spread for each configuration, and we see that the flame spread correlates very well with the emissivity of the chamber walls. So when we consider these results in conjunction with those for uh, the round robin test, as well as the new chambers from the same supplier, uh, when we plot these results on this correlation between flame spread and emissivity, we get a very clear picture. Uh, so on the extreme left of this plot, we have the flame spread from the round robin tests performed at different labs within the EU. Uh, this value falls close at 1.5 meters, which indicates that these chambers might have significantly aged, uh, and the value, the flame spread results from the new chambers from the same supplier fall uh, at a value of about close to 2 meters, indicating a very low emissivity. So essentially, these experiments helped us uh, explain the dramatic effect the emissivity of the chamber wall can have on the flame spread, and essentially they help us explain why we were observing this difference between the test results from CTCB and those from the round robin tests. So in conjunction with uh, experimental work, we also were performing theoretical modeling of these processes uh, in using computational fluid dynamics. So these were performed in a CFD tool called ANSYS Fluent. Uh, we considered the cable material in a simplified geometry in the form of rectangular slab, and the degradation of the cable material as it gains heat was modeled as a first order chemical reaction, is shown over here. Using this model, we studied two cases of the chamber wall appearance, simulating a very new chamber with a very low emissivity of the chamber wall at 0.5, 0.05, and another state of the chamber with very aged walls at an emissivity of 1. These these models helped us verify what we were seeing experimentally. So from the plot over here shows the prediction of time variant heat release rate from the cable material during the duration of the test, which is 20 minutes. What we see is that as the emissivity decreases from unity to close to 0, we see a reduction in heat released from the cable material, uh, indicating reducing flame spread for uh, an aged chamber. Going further into predictions from the model, over here we look at the temperature of the chamber wall surface as predicted by the model. So we have two contours over here. On the right, we have the temperature of the wall for case with high emissivity. The model predicts uh, a very high temperature of the chamber wall material, especially near the burner, and basically this indicates that the wall absorbs significant amount of heat from the burner, leaving less heat for the cable to absorb and get paralyzed. On the other hand, for the case with very low emissivity walls, the chamber walls don't heat up significantly, and therefore that leaves more amount of heat for the cables to absorb and get paralyzed. Finally, using the models, we also made a prediction, quantification of the vertical frame spread during the test. In the model, we define the so-called burn fraction, which is a ratio of the amount of paralyzed cable at any given location to the total cable material available at that location. So on the right, we have contours of the uh, burn fraction in the cable material at the end of the burn test. A high value indicated by red color indicates that the cable at that particular location has completely paralyzed or has been completely degraded to char. And a low value of 0 in blue indicates that the cable is at that particular location is intact. It has not been affected by the burner flames. So what we see is that uh, for the case with low emissivity chamber walls, the total amount of charred the length of the cable till which charring happens is higher also than the case for high emissivity chamber walls. So basically, from the model as well, we predict a slightly reduced flame spread for the high emissivity walls. Further, at any given location, the width of the cable that is degraded or charred also is higher for low emissivity chamber walls than for high emissivity chamber walls. So these modeling results help further validate or support the hypothesis found earlier of uh, emissivity of the chamber was directly and dramatically impacting the flame spread result from burn testing. So with this, I'll come to the summary of this work. Through observations of several tests performed at the CTCB chamber over several years, a hypothesis was formulated on emissivity impacting the flame spread result from the burn test, and experiments were designed to test this hypothesis, which validated the hypothesis of emissivity having a significant impact on the flame spread result. And these results explain why we had observed the deviation between round robin results and CTCB test results between on the flame spread. Essentially, as the chamber ages over the long term due to repeated testing, the chamber was showing aging effect, increasing its emissivity and impacting the flame spread. They also explain why the new chambers show a much pronounced higher flame spread. The emissivity can be measured independently for chambers with slight aging, and further, as shown earlier, the walls can be coated with suitably chosen materials to achieve a high emissivity. Further, the results shown, experimental results shown earlier were qualitatively confirmed by modeling, helping the hypothesis. What's more important is that the test standard as it is does not address the impact of emissivity yet, and therefore this is something that may need to be considered for next updates in the EN 50399 standard document. So some of the next steps that might be considered for this work are implementing the coating for general testing, for implementing high emissivity coating for general testing for the test chamber. This is already been done in the burden test chamber for general testing, and some of the products that were certified earlier with less emissivity chamber walls are being retested to see how the changed emissivity impacts their flame spread result. One important aspect to consider for this is the durability of the coating, as it undergoes several iterations of burn testing. The coating material can degrade due to thermal degradation, and materials which can withstand longer or more number of tests are desirable. Having seen the impact emissivity can have on the flame spread, it needs to be discussed whether and how to include this into the test standard. In terms of other next steps, we are also working on improving the theoretical model discussed earlier. And finally, can it also be considered to check emissivity in other test chambers to see if that would explain the discrepancy in flame spread results from these chambers. With that, I come to the end of my presentation. I would like to acknowledge the tremendous support we received from our colleagues in Berlin for performing these experiments, Fred, Wolfgang, and Jani. and our colleagues across the globe for detailed technical discussions and suggestions during the course of this work, Angela, Praveen, and Natalia. So thank you all for a very patient listening, and I'll be open to any questions you might have.
Thank you, Hariam. Again, a very interesting analysis of potential impacts on flame testing for cables. An interesting thought. I remind the audience that if you have any questions, I see a couple claps going on, but if you have any questions for Hariam, please enter them in the chat, and we'll ask them of Hariam. A question that came into my mind as I think about a variety of both vertical and horizontal flame tests for cable. A lot of these chambers use ceramic brick or that kind of walls, as opposed to a metallic wall that has reflection and heat emissivity effects. With that, is there any impact on airflow distribution, or turbulence or anything like that that might be different from a smooth metallic wall versus ceramic walls or brick walls, if I may?
Yeah, that's an interesting question. I think that can be an interesting thing to consider from the cases, from our experience so far on studying theoretically these tests for with metallic walls. Probably they may not have an extremely different turbulence effect because of the overall magnitudes of flow velocities being on the lower side near the chamber walls. So it may not be, I mean, at least from the flow perspective within the chamber, it may not be very different for ceramic walls versus metallic walls.
Yeah. And I know that, in different maintenance procedures for tests where you're using brick, ceramic brick, that, every so often you've got to replace that because of the impact on not only heat just, profile, but also air profile. So emissivity, to me is a very interesting concept or measurement to see what is actually happening in the chamber. But this kind of leads into a question coming in from the audience. Different chamber manufacturers use different materials for their chamber linings. Some are shiny, some are rough. Over time, most of them get rusted in some way and need to be maintained. Will this have an impact? When chambers are new, you're going to get, one result in flame spread versus a chamber that's been in use for quite some time.
Right. Yeah. So as I discussed earlier, as the chamber ages, we can see a significant change in flame spread. When you compare two new chambers, they depending on the chamber supplier, if they have different morphology of the surface, they can have different results at the beginning as well. And both of irrespective of the chamber supplies, as the chamber ages due to repeated use, they are invariably going to accumulate soot and resulting into high emissivity surfaces later on, showing a reduction in spread.
Yeah, that how you do that and how you maintain the chamber is really critical to get consistency of results for sure. Is your recommendation for the chamber walls to be deliberately coated rather than regularly cleaned? I guess that's an interesting question between maintenance and coating.
Yeah. So since our results show that increasing the emissivity results in a lower flame spread, and right now, since the standard does not address this parameter of emissivity, the chamber can be coated to help reduce the flame spread. And as we discussed already, this is the emissivity is a critical parameter, and it should be addressed. It should be taken into some account in the standard document. And if that happens, then one of the things that may also need to be considered within the standard is how to maintain the chamber walls to the same emissivity level as time progresses. So some of the things that may need to be thought about us are how to maintain that, like what should be the frequency of these maintenance activities and so on.
And I'm not sure if you addressed it, but for these coatings, would these coatings be for very specific metallic walls, or would these coatings also be for other types of wall materials?
So
Could you?
right. So as far as the test standard goes right now, it does specifically define what kind of wall materials can be used. So I believe it's stainless steel walls with certain thickness. So so that part of it is already considered by the standard in some details. So with that, the coating material has to be something that works well with these materials, with these metals, which are currently being used.
Right. Okay, I don't see any more questions unless someone from the audience has a last minute question. I certainly want to thank Hariam for his time, and of course the research and the evaluations that went into this paper and this presentation. A lot of complex parameters clearly go into fire testing. It's not an exact science, but certainly it was very interesting and an important topic. I don't see any more questions, so I will provide the contact points for her. Let me just switch here for you, and here we go. Very good. Hopefully you can see that. Is that showing up there for you? Okay. So if you wish to reach out to Hariam to talk further, or perhaps to request some of the data contained in his presentation, please contact him through his email address. And again, each of these IWCS webinars are recorded and will be archived on the IWCS.org website. And it normally takes about a week or so to get this up and running, but feel free to share that link with your colleagues to review this presentation again. The IWCS webinar series will conduct technical paper presentations as well as some sponsored company events each month. And our next scheduled IWCS webinar, it'll be a technical paper presentation, will be on Friday, May 17th at 10:30 a.m. Eastern USA time. Each of you will be receiving an announcement for these events. So please feel free to share these announcements with your colleagues so that they can also join in and register as well. I don't see any last minute questions. So before we conclude, I want to make sure that we all recognize and thank our IWCS partner sponsors who contribute greatly to the success of our Cable and Connectivity Industry Forum. Without their strong leadership and generosity, we would not be able to bring these important technical innovations and information to you and our global community. So again, we thank you to all these leading suppliers, including Corning, to our industry for their immense support. Again, I want to remind you that today happens to be the deadline for receiving abstracts for our IWCS 2024 event in October. There always are a few late stragglers, but if you are interested in presenting a technical paper, please go to our website. It's very simple to enter a one-page abstract for us to consider. We'll be getting together as a IWCS team next week, actually, and we'll review these abstracts and come up with a preliminary program for the event in October. So you also have opportunities to exhibit, and certainly we hope that you'll consider attending the conference and be able to network with all of these important presenters and your colleagues from around the world. So our conference will be at the Rhode Island Convention Center in Providence, Rhode Island. We'll be returning there for our 73rd annual cable connectivity event. So please watch your inbox, your social media, and also our website to learn more as these exciting sessions become known and become available. So please tune in to IWCS.org for more event details. Have a great weekend, everyone. Hariam, again, thank you so much, and we'll see you soon.
Yeah, let me take this opportunity to thank David and IWCS for me to present this work. Thanks a lot.
Thank you. Have a great weekend, everyone.